Hello everyone. Actually, I don't even know if anyone has joined so far because I'm using OBS Studio here. Apparently there is someone in the chat. Oh, that's nice. So this is my first stream, so bear with me. Let's hide this very fancy note here for now. First lesson exiting Vim. Okay, so I just joined the developer support program from the RISC-V Foundation, and they sent me a development board, which is called VisionFive, and it's made by StarFive, and it's featuring an SoC, which has been designed by, I actually don't know whom, and the core is made by some other five again. There are many fives in the RISC-V world. So this here is the package I got. It's a very compact little box. And of course, I already had a look inside to make sure it's just intact, at least judging per the package. And what I haven't done yet is unseal the inside of it. So let's see. The first thing you may recall or recognize is this logo here. That's the logo from, I hope I'm pronouncing it correctly, RISC-V, who are famous for creating development boards, mostly based on Rockchip chipsets. And now we got a different one. In the box, we also have this here. It's a plug, which is for the US. So, little reminder here, the US is not the center of the universe. I'm in Europe. We have safer plugs here. Do not use those. Anyway, we also get a cable with it. It's just a regular USB-C cable with a USB-A plug, of which I have hundreds anyway, so we'll just use a different one. And then we got an SD card, which is just a regular micro SD card. Nothing too fancy. I will probably not need it today, so I won't bother opening it for now. And the final thing here is the board itself, the VisionFive. So this is now the actual unsealing. I guess it will take me a second. I'm sort of prepared though, so let's cut this open actually. At least it's sort of hand-friendly packaged, so it's not too hard to open. And if you haven't heard about this board, I actually prepared something so we can have a quick look at that. There is this website here, the StarFive website, where they're presenting the board. It's actually, I think, the first board, and it's based on another one, which is called BeagleV by the BeagleBoard team, which you may know for the BeagleBone Black. So BeagleBoard made the BeagleBone Black. It's all a bit confusing. Yeah, sorry for the small image in the camera. You won't see many details anyway, because it's not like the most excellent camera here. I would just stick with showing you things on the website here for now. Now, of course, this here is just marketing, blah, blah, so we don't really care about that. I just scrolled down at some point and found this here, a link to the documentation and some SDK. And when you read SDK, scream and run away. You don't need that. All we need is the documentation. So there was another link here to the board, and this here shows you the actual board itself. And this image is by far greater than what I could ever show you on my camera. Let's actually zoom in. So it's upside down, but you can see it's made by StarFive. Down here, and this will be very important for our development purposes, we have a so-called SPI flash. That is, you can imagine it like a little USB drive or something. It's really just the storage part. And you can talk to that through a bus which is just called SPI or SPI, as some people say. And SPI is short for Serial Peripheral Interface. So we need to program something to talk to that eventually, maybe. Not for now though, that's just a note for later. There is a pin header here, which you may recognize from the Raspberry Pi. So they even colored it, so it's easier to recognize everything. The red pins are the 5-volt pins, while the yellow ones are 3.3 volts. Both very, very handy to have because they are used for many, many different things. So if you want to attach actual peripherals, you will need those. You may sometimes need other voltage levels, but yeah, then you would need to do something else. The black pins are the second most important pins. That's the ground pins. Whenever you need to connect something which is like, I don't know, something on the outside, you will always need to connect the ground pin so that you have the same base level for the voltages, because voltages are just, I guess you learned that in school, but anyway, they're just differences of potentials. So that also means this 5-volt pin here is relative to the ground pin next to it. So if I were to use something, whatever, like my socket here in the wall, I would have a different base potential, probably, right? So if I were just to connect something and I was missing the ground pin, let's say I'm connecting an image sensor, like for a camera, and I don't connect the ground pin, I will probably not even be able to talk to it. So yeah, so much for the board so far. In the middle, you can see the actual SoC, that's the system on a chip. Or, back then we were talking about something called a CPU or a Southbridge in the home computers. Imagine all of that combined in one thing, and also the chipset. So from that chip, we can already talk to the external peripherals, like the pins down here. They're somehow connected to that, and I hope we will find schematics so that we can actually see that. Same with the flash part. So that's where the chip will eventually load its firmware to boot from. And then next to the SoC or SoC, we have two chips which look very much like DRAM chips. I think I recognize them to be SK Hynix. That is one of the companies making DRAM. And that's probably, I would guess 2 gigabytes each, because the board is spec'd at 8 gigabytes. But it could also be that there is something else at the bottom. Anyway, in the meantime, I managed to open this here. And the board is actually quite large. So if you know the Raspberry Pi form factor, this here is like, let's say 20% bigger in size. So essentially, if you were to, I don't know, create a cluster or something, you would need to deal with this different form factor in a way. So I'm talking to some people who are developing SBC-based clusters, and yeah, this would not be a suitable option, so you would need to make a different board. But this here is mostly targeting developers, so you have like tons of connectors, which you probably wouldn't need in that case anyway. All right, so here's the board, and I can now read and verify actually what's written on the chips, which I identified as DRAM, and indeed it's SK Hynix something. There are two here, only two of them actually, nothing at the bottom, which means they would be 4 gigabytes each. Or maybe I was just misreading the website and it's not 8 gigabytes but 8 gigabits, but I don't think so. So let's actually see what they write here. This here is the documentation archive on the website. And let's see if we can find any details on the product. So first of all, we're on Twitch here, a streaming platform, I think mostly targeting gamers. So we're a bit of a snowflake. But anyway, they are suggesting to play Chocolate Doom, whatever that is. I know Doom, the good old computer game, which runs on very shitty hardware even. And then they also suggest playing Quake. Yeah, I would say it's about from the same era, also a very fancy 3D game. Then here is a 40-pin GPIO header user guide. So the GPIO header is this fancy header I just described, which has the many colors. So all the green pins, and I don't know what blue is for. Anyway, the green pins are the data pins, which you can use for mostly almost anything. We will have to verify with the documentation what precisely we can use it for. It won't be too interesting to us, but we will need one of them at some point to verify that we can actually talk to the pins here. And this GPIO that you see here is short for General Purpose Input and Output. So those pins can be used for sending data in two directions, right? So you can retrieve data, that's input, and you can send out data, that's output. And the output mode can be very, very nice for just a very simple, like a heartbeat check or something. So you can attach an LED and make it blink, or at least light up so that you have some indicator that your code is actually running when you're writing low-level code, which is what we intend to do here. Okay, now I don't know what SHTC3 would be. I'm not familiar with that term. IIC, that is probably short, well, usually we say I2C, that's the inter-IC or integrated circuit bus, which is a very simple bus to talk to peripherals, similar to SPI, what I described before. And another one here is UART. So UART is the universal, I think, asynchronous receiver and transmitter. So that's a very simple way of sending and retrieving data, like you would know from an emulated terminal mostly. We can do this over a UART. So imagine you were running a system like Linux or FreeBSD or Plan 9 or something, or Illumos, and you wanted to have a serial console. Then this would be the hardware to use for it. Now they have some tutorial for a specific application here, reading GPS data. We wouldn't be concerned with that at our level here. They also fancy Node.js application development. We don't care about that either. And there is a quick start guide, which I hadn't actually looked at. So let's open that in a new tab. And then there is a PDF here, the technical reference manual, which I already downloaded. Okay, so the quick start guide, let's have a quick glance here. I guess it's not very verbose and not telling us very much. Oh look, it has this nice watermark here. That is actually very common for especially hardware datasheets. So hardware vendors, for some reason, are very scared of sharing any information. And that's why usually you see things marked as confidential, even for public documents that they publish themselves, or having these watermarks or whatever. This is not like, you know, just putting a logo somewhere, because you could as well put it here in the corner, or like here, have the link to the website below. Anyway, as we're used to reading, no liability, whatever, no warranties, whatever. So let's see, what else do we have here? So it looks like this is mostly usage guides. They have a history of changes here, which is on doing setups on various systems and so on. Something Rawhide, that is a Fedora Linux-based environment, which is a very high-level thing. So we're not doing high-level things here. We're going to work on firmware. And firmware is what comes far before Linux, or whichever operating system you want to use. Could also be Oberon. There is millions of operating systems anyway. And what we are going to do is, we're going to write something which would be able to start any other operating system. Okay, so let's look at the overview. There is a hardware overview here. Features and specifications, that can be a very brief explanation of the features, I guess, like the peripherals again or something. And there we go, pinout diagram. The pinout diagram is what we're mostly interested in for now, because it gives us a clue of what we're actually looking at. When we look at something, there are lanes on this board which, you know, are very hard to trace with the human eye. But if you have documentation, that is excellent, then you can actually follow that. So that is what we are definitely going to look at. And then there is this getting started guide, like flashing Fedora to some micro SD card, which I said we're not interested in, so I put the SD card aside here for now anyway. Windows, Mac, Linux. Unfortunately, no documentation for FreeBSD, OpenBSD, Dragonfly, Illumos, or Plan 9, or any of the million of other operating systems. That is also very common, so people mostly assume that you run specific operating systems, which is a bit sad because, you know, choices are not restricted as much. So yeah, we don't care about this. This is very high level application stuff. We don't care about that. But this here is very, very interesting. The boot flow. So we're going to write firmware and we will need to figure out where we can start. So if you imagine, let's look at this here again. This chip here will have something which is also known as a mask ROM. More commonly also known as a boot ROM sometimes. But what it means, and that's why they call it mask ROM, is the part of the firmware that is really firm and not changeable at all, which is part of the chip itself. So it's an actual hardware part. Sometimes that can also be a bit of a lie, depending on the vendor, but essentially that's the idea. There will, regardless of how you put it, there will always be something which is starting initially. And depending on the vendor or the specific chip, it would start reading from different peripherals, like the SPI flash down here. So this is where we will likely put our firmware. Okay, there is some more sections updating firmware, recovering the bootloader, and they're describing something on U-boot. U-boot is a project which does the initialization before an operating system like Linux, for example. And depending on the platform or the vendor, it can be that it's sufficient and everything is implemented there, or they may have some other component again. So we will have to figure this out. So regardless, we will probably not read too much of this. It's quite brief anyway, but it's good to take a look at that to see how their implementation of U-boot works and if there is something that is useful to us. And well, eventually they have some repositories here, so that might also be interesting. And I hope they offer more data sheets there. So you see I opened 2 more tabs already. And this here is the JH7100 datasheet, which is the actual SoC. So if you look at the image again, you don't see it written here. Do I have it here? Yes. Here it actually does say JH7100, and it also says U74X2. So U74 is the actual processor core, and then the JH7100 is the SoC around it. So you can imagine if you were to draw a diagram that you would have this, you would have these cores, somehow in the middle, and then around that you would have something that connects them and that also connects the peripherals, such as the GPIO, the SPI flash, and you can already see there are tons of more peripherals here, like an HDMI port, USB, Ethernet, and this is probably for speakers, Wi-Fi, and so on. Wi-Fi can be attached through different means. I assume this one here is attached through SDIO, which you may know from SD cards. So yeah, it's one way of connecting SD cards at least, and also one way of connecting Wi-Fi chips. All right, so that was a very, very brief overview. Might have been a bit fast, so if you recap the video, you can maybe follow along again, or just open all of those links yourselves. So this here is all on their website, starting on starfivetech.com, and here you have the documentation again at the very bottom. And they also have actually the link to the RV Space website, which is where you find the JH7100 datasheet. Okay, so now the first thing I want to do is, since we already got this quick start guide here and we found something interesting, Let's actually start over here. Let's start with the hardware overview before we look at the features and see if we can recognize something. So here we have the board again with a slightly different picture and also the bottom side. So yeah, as I told you, I just had a look at the real thing in my hands here. There is nothing further here at the bottom. So depending on the board, you may sometimes find something like extra chips here. It can be DRAM, for example. But you can recognize this here at the side. You probably have seen this before. That's a micro SD card reader. So if you were already wondering where I would put the SD card here on this side, yeah, it's just at the bottom. So let's zoom in again. There are numbers here, and do we have an explanation of the numbers on the same page? No, of course we don't. So we will have to look at that in a second. Let's see what numbers we actually got. So we have 4. 4 is the GPIO header that I already described a bit. We have 1, the SoC. 2, the DRAM chips. Where is 3 actually? Here. 3 is the Wi-Fi. Then we have these connectors here, that one, 5, and those two here, 10. Those are for flex cables, and probably they are for cameras and maybe display, or sometimes even used for microphone arrays or something. But yeah, it also just depends on the board. And now I can see also what's written here. This says fan, so it's not, as I assumed first, anything like an audio port. It's for a fan. So now we also know where we can attach this nice Ragja fan that they also put in the box. And I would need to mount that. But we're not going to do that now because we're not going to power on this board today. We're going to save this for another day. And I can already see something which is also a bit harder to see here in this document, but you can see parts of it. Here it says debug. So this interface here, 3 pins, that is one of the UART interfaces. And this is where I will have a serial console once I'm at that point. Those 2 buttons here, they're also very important. The right one is reset. You can still read that, I guess. And the other one here is called something boot mode. And that suggests to me that when I keep this button pressed and I reset, or I keep it pressed while powering on initially, I assume that this chip here enters a specific mode so that I can talk to it through some whatever software tool. And I'm not sure yet how I need to attach that, but we'll figure this out. And also note this row of pins here, which are unpopulated. We might want to do that ourselves. So we would need to solder a bit, which is also why I'm keeping the fan off for now. That would be the debug interface, like the real deal, which is called JTAG, which is just actually not short for any port or something. It's the Joint Test Action Group or something like that. That's like a standardization body who are releasing standards for, well, testing chips essentially. All right, down here, I guess you recognize all of these ports. This one is a bit odd. That's the HDMI port. Usually you would have this horizontal, but this here is mounted vertically. We got Ethernet, USB again. Oh, we got the audio jack here. I'm not sure if that's microphone and output, but I guess it's output only because it only looks like, yeah, it's only output, so no microphone here. Well, whatever. We got this here, a USB port, and I hope this will be a debug port or something, which is for talking to the chip, but it's not labeled here on the physical board. So we will have to figure this out now. Okay, so with all those numbers in mind, let's see if we recognize everything correctly. First of all, note this here. 4 gigabytes, this is an uppercase B, and uppercase B is for bytes, otherwise it would be bits if it was lowercase, but this is uppercase. So each chip is 4 gigabytes of DRAM, and that gets us the 8 gigabytes in total, which I already read somewhere on the website. The SoC itself, which has 2 U74 cores, and the SoC itself isn't spelled out here again, but they're stating what the instruction set is, and this is something which is very specific to RISC-V. So if you're used to other architectures, like ARM, for example, ARM has different revisions, which are extending or changing the instruction set over time. Like there is ARM v6, v5, v7, whatever. And in RISC-V, they have these extensions and basics. So the basic architecture here is the 64-bit RISC-V architecture. And then behind this here, GC is actually a larger acronym. And GC is short for IMAFD, if I'm not mistaken. That should be the G, which is for integer multiplication, atomics, float, and double, which means we can do lots of different arithmetics. And the C would be for something I forgot again. And because we cannot remember this, we look at Wikipedia and we say wiki RISC-V. That brings us to this website here, which has a very nice table where you can see all of those letters. So yeah, G is short for IMAFD, and Zixer, and whatever that is, Z, I see something, some special instructions. And to be honest, I don't care too much because this is mostly for compiler engineers, but for me as a developer, it's important to know if I need to do float operations, that I actually have the FD part here. Yeah, I forgot what this is exactly. Maybe this is actually the explanation for it, but yeah, who cares? Yeah, I explained the R64I, so I is for integers, integers as in numbers. So that is very essential to doing arithmetics. Otherwise, any CPU core would be pretty pointless because, you know, everyone is essentially doing arithmetics. The 64 means 64-bit register width. So you can now use 64-bit integers for performing the operations. And as you can imagine, only having numbers but not having any operations is also pretty pointless, which is why we have the M for multiplication and division. We got the A for atomic instructions, F and D for floating point, single and double precision. Now you may ask, where do you find the addition and subtraction? I guess that is already implied here. It's not explicitly written, but yeah, you can read this up yourselves. All right, so now we know what this chip actually implements, right? At least the processing core. So if we want to see what else is in the SoC, we're going to look at this other data sheet, but let's stick with this one here for now. So we already identified the Wi-Fi and apparently Bluetooth chip, which is also not going to be interesting for us for now because we're not application developers. We're working on low-level firmware now. And when I say applications, I mean applications at large. And if you were very generic with the definition, then firmware is actually also an implementation of an application. But yeah, let's ignore that fact for now. The 40-pin GPIO header, we identified that. And now we got this here, another acronym, MIPI DSI connector. And that is typically for, if I understand correctly, display. So I think the D is for display. And then here we have MIPI CSI, and C is for camera. We already identified HDMI. We got Ethernet. It's a gigabit Ethernet adapter. That is okay. I don't actually care about the speed too much, but gigabit is just fine. We got lots of USB ports, 4 of them. we got something called a PMIC. PMIC is probably a power management IC or integrated circuit. So that is a chip that you can use to instrument the power on the platform to, for example, save some power if you're not using some of the peripherals. But yeah, we would have to look closer at the documentation now. Okay, so the audio jack here, it turns out it's a 4-pole stereo audio. Output only. So 4-pole means for each of the outputs, right and left channel, you have a dedicated ground, which is good if you want to have better audio quality. Eventually, so the USB-C connector, I already said we would need to see what it's actually for. It could be that it's really just USB-C, but it could also be that it attaches us to something which is in the SoC here. LCD to HDMI, okay. I'm not sure what that is about. Let's see what 8 was. 8. This here. Okay, so apparently the StarFive chip itself would have LCD output, and then this chip here would transform that to HDMI, and then it would end up here in connector number 9. That is how I understand it. We found the micro SD slot and the fan header. Well, the fan header is this here. So I would plug in a fan here, and then I would mount it through those 2 holes. And there is probably something for the SoC itself, like, you know, I don't see anything here actually. Sometimes you would use solder paste, or there are also these fancy new things now, which are like a piece of rubber. Anyway, so let's look at the pinout diagram. Now we're looking closely at the 40-pin header. So we got the 5-volt pins here. As I told you, the red ones are 5 volts, and the yellow, here it's slightly orange, the yellow pins are 3.3 volts. And then we got a bunch of GPIOs and some ground pins here and there in between. And if you remember from the image, there were also 2 blue pins. And now let's actually see what those are. They are the 7th pins from the bottom, and they're GPIO 9 and 10. I don't know what specific meaning there is to those. We will have to figure this out. Could also be that it's meaningless and just for orientation. I'm not sure. Okay, this here is also important for GPIO pins. They have a maximum current. So if you wanted to use them to supply power to any peripherals, don't do that with peripherals that consume much power, because you would run into issues. So if you were to do that, you would need to drive something, I don't know, like, you might know the WS2812 LEDs, which sometimes come in stripes of, I don't know, 50 or something. They would draw many, many amps of current. And this here is for 39 milliamps only. So instead of drawing power from here, you would use a dedicated power supply. And remember, connect the ground, because otherwise you would have different potentials. All right. Yeah, the maximum current draw when all GPIOs are combined should be less than 100 milliamps even. So yeah, if you were to connect a bunch of pins, you know, you would need to be very careful. All right, so all GPIOs can be configured to support different functions, including but not limited to SDIO, the SD card I/O interface. So not SD card, but whatever SD is short for, which can also be used for SD cards. Audio, SPI, I2C. Those 2 are the ones which are used a lot in embedded peripherals. UART and PWM. PWM is a specific output mode. It means pulse width modulation. You can use that to drive a motor, for example, which you shouldn't attach directly, because as we learned, you can only draw low amounts of current. So you would probably use something like a transistor or something to supply the power on the one hand side, and then to drive it from the other side. Okay, and then they have another user guide. So this here, I think we also saw it here in the list. Yeah, that one. That should give us more details. But for now, this here should be sufficient. Getting started, we don't care about this here. So attaching the fan, I mean, that's very intuitive anyway. We don't care about Fedora because operating systems are too high level for us, especially this stuff here. It's very nice to have this application, but that is for people who are, going to run the final product eventually. But we're developers, we're going to write firmware for this. Okay, so let's skim through here. Do we have anything else which is interesting? Nobody cares about SSH or anything. Here, Appendix B and Appendix A. Okay, now this is the first very, very interesting chart we're looking at. It looks very complex. So first, let me get rid of some decoration here. The boot flow, it starts with the firmware up here at the very top. And you can see they have some concept which is called second boot. Why does it start at second? If you remember, the actual first part is in the SoC. So that's why they start counting at 2 here. And 1 would be the actual chip, the hardware part. So there should actually be an arrow going in here. This would require something called bootloader whatever bin.out using their pre-made firmware, which we're not going to use. We're going to write our own. They would hand over to a next bit, which they call DDR init. DDR is what you also know as RAM, random access memory. That's what the R is for. And this is what we also will need to do. We will need to initialize the DRAM. So if you are used to, just powering on your computer, there is already a firmware component doing this for you. But here in this case, we're going to do this ourselves. So you can imagine there is some pins which are going to the DRAM chip, or chips. Here in this case, we have 2. And then you have a DRAM controller. And the DRAM controller is part of your SoC. So from your processing core, where you execute your code, you would need to start talking to this. And we're going to see how that works probably in the next stream already. Anyway, so after these 2 components have done their parts, they would hand over to something called OpenSBI. And this also comes specifically from the RISC-V space. SBI is short for Supervisor Binary Interface. I will show, in another stream, I will show a closer look at that. And we're going to understand what SBI really does, because here it's, a very high level overview only. OpenSBI is one implementation of SBI. But you might have heard that today we're not writing C code anymore, and this is implemented in the old language called C, which is about twice as old as I am. Instead, we are writing firmware in Rust nowadays. And that's also what we're going to do here. And luckily, somebody already created something which is called Rust SBI, which we're going to use. And then we're also going to skip this part here. U-boot is essentially then taking over from OpenSBI and setting up some environment which, if you think of your laptop again, is a bit like where you select the interface or the storage to boot from and so on. This is where it starts to understand concepts like files, for example. But we will not need this. Our part will replace everything up here, and then we are done. And instead of loading U-boot, we will directly load a Linux kernel. How we're going to do that is for later. But first, think of all of this here going away. We're going to remove 3 components and replace it with one component which is written in Rust. And instead of jumping from one component to another, we're just going to call functions, which makes the boot flow inherently easy compared to this here. Because you need to understand that every time you jump to something else, you will need to have a very strong contract of what you have done before the other component. Otherwise, the other component must assume that there is something already broken, and they would need to redo the work that you have already done, which defies the purpose of having the other component before you. So if you know your laptops, for example, you boot them and you run Linux, sometimes you see error messages about something called ACPI, and then the Linux kernel would patch the ACPI, which is the power management interface, just to be able to properly handle the platform. So yeah, if firmware has bugs, then the operating system will need to take care of that. And if you have more and more components in your firmware, there is more that can go wrong. And that's what we are going to avoid, which is why instead of 3 components, we will only have 1. All right, long story short, this down here is high-level stuff. We don't care about this, okay? So this is for Linux kernel, and this chip here is already supported in the mainline upstream Linux kernel. So if we go to kernel.org, we will find support for this already in Linux. And with that, let's skip on to the next page, which is briefly describing where you can find these components. So these bootloader, DDR init, and uboot are essentially what we just looked at and what we're going to replace, or just omit and leave out. These are links to GitHub. So if you look at the bottom, the link there, it says github.com StarFive tech, and then JH7100 second boot and releases. So they want you to download the final releases, but we're not going to do that. Then they suggest using a UART adapter here for the serial interface. So as I already described you, that's one way of connecting to a serial console. Like if you have the Linux system running on this chip here eventually, then this is how you can connect to it from the outside. You can just plug this into your laptop and then use your terminal emulator to talk to the system on the other side. If you know SSH and you're mostly used to networking, this is what you do before you have networking, or anything else for the matter. All right. We are probably not going to use this port though. So as I already showed you, there is another pin header, a 3-pin header, which says debug. And it says GND, RX, and TX. Just like these here. GND is for ground, RX is for receive, and TX is for transmit. Let's see which one is which here. Okay, this one here is transmit. No, this here is actually receive. They're crossing here. So receive on this side means transmit on that side, right? So what you transfer from here is received on this side. So if you connect one of these, it might be intuitive to say TX goes to TX and RX to RX, but no, you actually have to cross them. All right. So yeah, again, software setup, we're going to skip this part because we don't need this. High-level stuff here. Let's see if there is anything else which was interesting here. It's only 39 pages anyway, so this is really just a very brief look at this. A full manual for an SoC is usually among the thousands of pages which you might have seen if you already played around with something like Arduino or something and you looked at the chip documentation. Look, this is nice. So they implemented those buttons here, this boot button, or you could also say boop button, because you need to boop it with your finger. So if you boop this button and then you plug in the cable, you end up in an interesting mode apparently. So let's see. The baud rate should be 9600, which is very low. So mostly we're using 115 to 100 today. So this here is a very low baud rate, but that's okay. It's just whatever they baked into the chip probably. And because I skimmed through this here, let's actually read quickly. Before you recover the bootloader, so we're now before the bootloader, which means we're now talking about what's running inside the chip itself. You need to have a serial communication software on your computer in order to communicate with the VisionFive. We will use, no, we're not going to use Windows. We're going to use something on Linux because it's a system that actually works without blue screens. All right. Now this here is interesting. So it looks like they have an interface which is already using the serial console. And you already have something where you can type. And they want you to type load and then something. And this something here is a memory address. So we will have a very brief look at the datasheet for the SoC to figure out what this address here means. Anyway, they're saying when we load this memory address, we should see C, whatever. And then we would be able to use X modem transfer and then transfer a file. So I assume that that would write a file to the SpiFlash, which is interesting. So another option to do that is to use a programmer. And for the programmer, you would need to have a clip such as this one here. And this clip can also be attached to the SpiFlash chip. So you would open this clip like this and then eat the chip, which is very healthy. All right, so we might not even need this here. But it's good to know that there is this mode. And what's also interesting is you can use this mode to load some memory address. So we will see how useful that is for, just getting something to run without even having anything on the SpiFlash. Actually, we can verify that this here works by... I wanted to skip that for today, but let's actually party. Let's actually connect this board in a bit. Okay, so more blah-de-blah-de-blah. Reset pin, another boop button. So you boop the reset button and then the board resets itself. And then probably it just tries to, yet again, power up. And this here is interesting. Now it says JTAG and PMIC. Interesting. Maybe it's on power management overall. Who will see? All right, so here's another screenshot. And then there is downloads for binaries. Binary for recovering SpiFlash. Interesting. Okay, and that's the end of it. So let's scroll up a bit again. And let's see what this memory address that we saw actually means. So we have 18 and then 6 zeros. And for that, we're going to look at the manual, which I already prepared here. So let me pull this over here. So this here is now the technical reference manual. Let's see if they have some documentation of the memory here, but I don't think so. Okay, that's not the case, so let's look at the chip documentation here. Datasheet. Sounds good. There is also user guide. I don't know what E24 is. We'll see later. Okay, I think this is what we were looking for because it has... Oh, no, it only has 137 pages. That is also too brief. So we're going to have to look a bit more. Memory and storage. Interesting. Very brief notes. So what I'm now skimming for is, I want to find some table where we find the memory map. And the memory map would tell us which peripherals are in the memory, because the memory is not just the memory, but it's also a means of accessing peripherals, such as the SPI flash, for example. So there is probably something where you can write to some registers to access the SPI flash. This is interesting. IP blocks. Okay, we just found another interesting table, and this is something that you will rarely find from any chip vendor. Like Intel, for example, would never disclose this here. At least currently they don't, because they are closed, you know. This tells you what the specific parts are and where they come from and what the vendor is. There is some peripherals from Cadence. Cadence is one of the very famous ones. There are a few others, but this is okay. This is for all the, let's say, the fancy interfaces, if you will. So vision computing processor, I'm not into that too much, so I don't really care. And then we have the camera and display interfaces and USB controller. I also don't care too much about that, to be honest. Then from chips and media, what do we have? We have video decoder and encoder, which is interesting. So if I were to stream, let's say this Twitch stream here from that device, I could probably do that already. It has a JPEG encoder and decoder, which is also nice because it gives you acceleration. If you implement this in software, it works, but it can be very, very slow, especially on a low spec chip. Okay, and now everything else here is from StarFive. So let's resolve the confusion again. StarFive made the processor cores. VisionFive is the name of the board. And some other 5 made the board. Or the SoC. I don't know. That didn't really resolve the confusion. I hope you're not even more confused, because I am usually. Okay, now this here is also very interesting. NVIDIA. You know them from usually GPUs that you put in your desktop machines to get, you know, very fancy high resolution graphics and so on, so that you can play your 3D games and so on. So they made the deep learning accelerator. So yeah, that is for machine learning stuff, which I also don't care about for now, but could be very interesting for special applications. And we already know what DRAM controller we have. That is also very, very interesting. Open Edges. I don't know Open Edges technology. So I hope we can find some information on that. And we even got the version of the hardware, or of this core part. And now let's get back to one very fine detail. You see this here, IP. This IP is not for Internet Protocol. It is for a concept which is very hard to understand if you know, are a good person and you don't believe in hierarchies and so on. The idea is intellectual property, which means that whatever idea you have, you can even share it with other people, but it's still your idea. And if anyone were to pick up your idea, you would be able to control what they do with that. That's the idea. For some reason, it made it into laws, and it's actually legal to restrict whatever you can do with a product. It's a very sad fact. And maybe we need to work around that in some places, but for now we don't really care. And to be honest, I didn't understand that concept myself. So when I was facing this term here, IP block or IP core at some point, I needed a very elaborate explanation to understand the idea. And then I understood it's a very shady idea. But unfortunately, that's what hardware vendors do. In open source, we don't do this. We make our intellectual property open. We share it with other people. We let other people contribute it and enrich it. And then we get better products out of it. All right. So now we did a very, very deep dive into the hardware. And let's get back to the promise of actually playing with it, which I just made. So I said, we're going to connect to this now. And so what we're going to do is, I have a terminal emulator open here. We're going to use a tool that is called Minicom. And with Minicom, we're going to talk to the board, which means I first need to supply power to it. And then I also need to attach to the UART header. So I have this here. It's just, you can get this for a few euros. It's just a regular USB to, it's usually called USB TTL or USB UART adapter. Essentially USB on the one hand side, on the other hand you have the serial pins to connect to a UART. So now we need to connect this correctly. The wires I'm using are colored, so I don't mix them up so easily. There is one which is gray, which I'm using for ground for GND. I got a blue one. The blue one is TX. And if you remember, we need to cross it. So TX goes to RX on the other end. And the green one is not connected. I have a purple one. And purple goes to TX. Sometimes you would need a fourth pin to supply power, but we're going to do that through the USB-C connector. And of course I did this in the stupid order, so now I need to fill it with the middle pin. All right. That's looking good. Let's plug this in. I have a USB hub here, so it's a bit easier for me to work with these things. So sometimes I even need to use a third or even a fourth plug, especially if I work with multiple boards at the same time. It can be very frustrating if you only have 2 ports at your laptop. All right, so and I have dedicated switches for them, so I can now turn on and off each of the adapters or whatever I connect. Now if I say ls USB, you will see this device here, the serial converter. That is what I just connected, okay? So I can now connect to that using Minicom. And now you will notice there is a number down here, 115 to 100, which I told you is what is a very common baud rate. And we're going to change this using the options. If you're using Minicom, you press Ctrl A and then O for options. Ctrl A is like the modal access key for menus and so on, and O is for options. And here we can set up the serial port. And you can see E is what we're going to change. Now we have another hotkey again. We're going to just press C to select 9600, but there are many different baud rates you could go through. Yeah, we're just using this as a shortcut. Now you will also note there's this here, 8 and 1. This means we're using 8 bits for each piece of information that we're sending over the wire. I'm not going to specify this any further now. There is N, and this N is for odd parity. Parity means there is 1 extra bit, which is for a checksum, if you will. So if you have these 8 bits here, so these are 8 bits, now you have another bit, a 9th bit, and the 9th bit is just the parity of these 8 here. Now the last part, 1, is for the stop bit. So there will always be one bit, which means this is where this piece of information ends. So we have 8 bits, the parity, and then the stop bit. So essentially each piece of it, if you think in like network terms, you know this concept of packets, you can imagine this like packets. So each of them would be like 10 bits long. Okay. So we're going to exit here. And I want to do something before I'm trying to connect the board directly. Actually, we will just power it on. I want to see if there is something on the USB port, but we will probably see something now anyway, according to the manual. So I'm keeping the boot button pressed, which I remember correctly is the inner button. Let me check. Yes, I'm keeping the boot mode button pressed, and now I'm powering on the board and I'm releasing. And you can see, just like in the manual, it says SiFive, and we have a hash, which is like a shell to us. And now let's see if we got an additional USB device. Do we have something which suggests something like SiFive or something? It doesn't look like it. Okay. So the only way for talking to the chip directly appears to be this. And now let's look at the datasheet again, because I cannot possibly remember all of those details. There was this, was it in the reference menu? No, it was actually on the website, right? Yeah, here. So they were saying, I would just type stupid window management. This is why I usually use i3, but I haven't set this up here. Or Sway, because Wayland is nice. Okay, so they're saying load, and then this here. So we can copy this and just paste and see what happens when we type enter. We're seeing CC. Now it's expecting us to use the file transfer X modem whatever thing. I can actually show this to you. So there is file transfer protocols here. And as you can see, there are many different others. There is X modem, which has this C here. So apparently there is a relationship. Maybe that's why they are printing CC now. And I could use this now to transfer a binary file from my machine over the UART interface and then have that loaded on the other side. But we don't care right now. So I don't want to go too deep into that, because I don't see how that would help us. I want to get back to another data sheet and figure out what this memory address actually means. And one thing we're going to do now very quickly is I will reset the board. I just did. Okay, now I don't see any output anymore. All right, that's this part for today. I'm now just closing this. And next time we're going to see if we can do anything more with it. But first, we will need to get more familiar with the hardware itself and read some more manuals. So that is always the hardest part, finding documentation. And when you have the documentation, read and find what you're looking for. So I think we already did quite well today, because we occasionally found a lot of stuff which is very interesting. But you could also see that, I'm not doing this for the first time here, so I have some previous experience from working on other stuff. So the final goal for today is to figure out what this memory address means. And the question is, where do we find this? So we have a clone of this repository here. That is from where I opened this file that we just looked at. Let's see if we have a memory map here. If we do, we are lucky. I will search for memory map. Oh, look at this. We're lucky today. So now you see there's lots of addresses, start and end address. These are ranges where you find different specific peripherals. So, oh, look at this here. There is some memory addresses which are for debugging. And now we have this here. It says internal ROM. Do you remember the address we just saw? 18 and then 6 zeros. Isn't that exactly what we were looking at here? 18 and then 6 zeros. Lucky winner, I would say. So this is the internal RAM and ROM and whatever SLV is, or SIV, slave in system. All right, so we figured that out. There is this range, int RAM 0, int RAM 1. It could be internal RAM, like SRAM. So SRAM instead of DRAM would be like static RAM. That is, as I heard, much more expensive. So that's usually smaller parts. And then DRAM is what you would usually have externally. And it would be, not as fast, but you could produce larger capacities much cheaper. All right, then we got some reserved spots, whatever those are for. This ROM part here, I have no idea if you can overwrite this. Probably not. But it would be interesting to copy this out at some point. So when we have an operating system running, we could dump this here, maybe, to our machine. And now comes the next interesting part. So we already talked about the SPI flash, and now we got 256 megabytes in size. It says off-chip QSPI NOR or NAND flash belonging to the JH7100. Now what is NOR and NAND? Those are different ways of producing flash memory. NOR is, I think, slightly more expensive. So usually you would have smaller chip sizes. Usually today there would be like 8, 16, sometimes 32 megabytes. So if you look at a current, let's say AMD or Intel board, usually you would have a 32 megabytes chip. And those would be NOR. Those are very durable and, close to impossible to break. Now NAND flash is much larger in size. And let's actually look at the board again. It's not written in the datasheet, if I remember correctly, or the manual of the board. So I'm unplugging this here. Now I'm taking a very close look to see what I can read on the chip. And I think that will be the last part for today. Unfortunately, I don't have a camera set up yet for showing this. But I do have something prepared, which we can look at some point. Just not today. All right, so I just identified the part. It's a Giga device, 128 megabits flash part. Giga device is one of the vendors making those chips, alongside Macronix, for example, is also very famous. And then there is Winbond and a few others. And 128 megabits means an eighth of that in megabytes. So let's see, half of that is 64, half of that is 32, half of that is 16. So this is a 16 megabytes SPI flash. And as I told you, I could use this programmer here also to read from it. Now, the problem with doing this in-system, and in-system means it's soldered on a board. If you do this with a programmer, it can happen that you're actually powering the board or parts of the board, and then something else, usually the SoC, also tries reading from that chip or even tries writing to that chip, which means that it would be disturbing for you to try reading it at the same time. So usually, what vendors do to avoid this is they would you know, have some diodes or resistors or something, you know, some circuit to isolate the flash part. I'm not even sure if we are going this far today, but I think we are. I'm just trying to read from this chip now. So I'm attaching my clip, which is a bit hard because this flash part, there are different form factors, and this here is a very tight one. So yeah, we'll see if this even works. So the clip is now attached. It's looking just fine, and I'm going to use one of the many other USB ports that I have here on my very fancy adapter. All right. And we are going to read the ROM by saying sudo flashrom -p. Now the name of the programmer, this here is based on the FT232. Future Technologies, they're making programmers like this one, or actually chips which can be used for many different things, but you know, flash programming is one of them. And then we're selecting a port that's specific to this programmer here. Now we're going to run this command to see if any flash part is actually detected. And it looks like, nope, it's not the case. Nope. So there are many valid reasons for this that are possible. I assume that it's just not attached properly because, as I told you, this flash part is, you know, let's say not very clip friendly. There are larger parts where it's easier. So yeah, I hope we will not need the X modem transfer mode because that's really horribly slow. Or I might just solder something to make this 100 times easier. Okay, I'm now trying to just hold the clip a bit to see if that helps. Nope, that doesn't work. Okay, so I guess we will have to figure out another way. Yeah. So if you remember, we were connecting to the boot mode through 9600 baud, which is really slow. And if you connect large files over that, you know, it takes too much time. So we will see if we can find some other means. A programmer would really be the nicest way and also the fastest from what I can imagine. Or maybe we can find out something else. Anyway, that shall be it for today. I hope I could give you a nice overview for a start. And next time, we're going to see that we can actually write something to the SpiFlash eventually, or at least load some file from my system over the boot mode, like the recovery binary that they're providing. But we're also going to try to write our own. And with that, our journey actually will start. So yeah, for recap, we were looking at the StarFive VisionFive RISC-V single board computer. And thank you for watching, and see you some other time.